Hello everybody, today we're going to be designing a up-down counter, a 3-bit up-down counter. So I already have the state table here. Let's just be clear what we're dealing with. This is the state table, and we can divide the state table here into two parts. So you'll notice that our X here is the input of the circuit. And let's say if X is 0, then we're going to be counting. This is our current state. If X is 0, then we're going to be counting up. So that's the next state. So let's keep going down. So current state is 1. Next state is going to be 1, 0. Current state is 1, 0. Next state is 1, 1. And so on and so forth. So what you have here is you're counting up all the way up to 7. So this is a 3-bit counter with the added benefit that it can go either up or down. So let's look at this one here. So it's best if we start from the bottom. So if our current state is, and we look at these 3 bits here, if our current state is 7, the next state on the right is going to be 6. And if we go up, current state here is 6, next state is 5. And obviously I'm just going to assume that you all know how to count in binary. So essentially what we have here is counting up when X is 0 and counting down when X is 1. Okay, so last time we spoke I actually went over K-maps, and I did the JK K-maps, but I assumed that you guys knew what a K-map is and how to circle it. There's a lot of material online about K-maps, and you can learn how to do it easily. So, and for this particular example, I'm going to fill out my own K-maps because it's only 3 of them, and then we're going to make our JK equations for each of these variables that we have here. So okay, so let's continue here. So I'm going to be looking at only these values here, and let's see, I'm going to be looking for wherever there is a 1. So there's a 1 right here, right to begin with, and so the 1 that corresponds to this is this one right here, right next to it, and we can see that it's 0, 0, 1, 1. So 0, 0, 1, 1. Put the 1 there. You move down. 0, 1, 0, 0. So 0, 1, 0, 0. That's a 1. Move down. 0, 1, 0, 1. So that's here, and then that's here. So right there. Just keep going. So I see 0, 1, 1, 0. So 0, 1, 1, 0, right there. And this one, 0, 1, 1, 1. So 0, 1, and then 1, 1, right there. Aha, but this is a 0 here, so it doesn't count. I can't write it down, so we erase it, and we keep going down the list. This one and this one. So we have 1, 0, 0, 0. So 1 0 0 0, put the 1 there. So let's not make the same mistake. We're gonna go down until we get to 1, which is there, and then we have 1 1 0 1. So 1 1, let's get rid of that, and then 0 1. So right there. Let's go down. 1 1 1 0. So it's the same one here, and then 1 0. It's gonna be right here. And then we have 1 1 1 1. So this one goes up here. So we have 1 1 and 1 1. Goes right there. Okay. So this is the state table of C next state. So we have to do this 2 more times. So I'm gonna go a little faster on the next one, but for now I'm gonna put this down here because we're gonna get back to it when we make our JK equations. So I'm going to go ahead and copy this, paste. So now obviously I'm looking at B next state. So the first one is 0, the second one is 0 0 1 0 0 0 0 1. So 0 0 0 1 right there. The next one is 0 0 1 0. So 0 0 1 0 right there. Next one is 0 1 0 1, and again I'm right here so far. So 0 1 0 1 right here and right here. So that's that. And if we move down, we have 0 1 1 0. So 0 1 1 0 right there. Keep going down. Here we have another one here. So that's 1 0 0 0. So that's this one. Just get rid of that arrow. And then 0 0 right there. So I put it here. And we keep going. We have 1 0 1 1. So 1 0 1 1 right there, and then right under that is 1 1 0 0. So 1 1 0 0 right there, and the last one is 1 1 1 1. So 1 1 1 1 right there. Let me see if I got that right. Yep, that's good. Bring it down. Copy that. Paste. And then this is going to be our A next state. Okay, so then we have a 1 at 0 0 0 0. So right there. And then we have another 1 at 0 0 1 0. So 0 0 1 0 1. And then 0 1 0 0. So right there. And then we have another one right here, and that reads 0 1 1 0. So 0 1 1 0. That's right there. You move on. We have 1 0 0 0. So 1 0 0 0. So right there. 1 0 1 0 for this one. So right there. 1100 for that. So 1100 for that. And then last but not least, this one here, which is 1110. So 1110 right there. Okay. Let me bring that down. Looks like I ran out of space, so I'll just have to bring it down all the way. Maybe about here. Right there. Okay, so now we can begin to write our equations, and like last time, I don't want to make long equations. I want to make this as easy as possible. So the best thing to do is to use JK flip-flops, and that's what we're going to do here. So we're going to start with JC, and if you remember the rules, we start where C is equal to 0. So my focus is going to be on this cell, or that set of cells, and this set of cells. So I'm going to skip a few steps. I'm not going to redraw the K-map. So you can sort of imagine that this cells are no longer here for now. And then based on the outer ones is what we can, when we can make our equations. So we see that there's a 1 on this column here, and there's another one on this column. So for the one on the left, we see that there is a 0. Therefore an x naught. So why is that x naught? That's because of this 0 here. And x naught, this is just a notation that says no, this is the inverted version of the x. So, or rather, you know, it's the 0 state, because this is logic design and things are 1 or 0. So this is the 0 version of that. And then we're looking at this one here, which is B and A, and it's 1 for both of them. So it's not 0, so we know that it's B and A, just like that. And then what we do is we add the other one. So here we see that the x here is 1, so we can say x, and then we see here that B and A are 0, so we say B naught, A naught. So that's the equation for the J of this flip-flop. So now we're going to be looking at the case when C is equal to 1, which is this one here. Let me draw with a different color. This one here. And then we're going to be ignoring these outer ones. Okay, so and again we have K naught C, and that's going to be equal to the circles that you do here. But as you know, we want to make our life easy. We don't want K naught. We're going to want just a regular K. So we say this, just K naught. And what we can do now is just circle the empty spaces like that and like that. So what do we got? We have a empty space right here where x is 0, so that's x naught. And then we have the case where B and A is equal to 1, 1. So B and A is 1, 1. And probably you already guessed by now, but these are going to turn out the same. The JC and the KC are going to be the same equation, the same expression. So if we look at this one now, we have x equal to 1, so that's x, and then we have B and A equal to 0, 0, so that's just B naught and A naught, of course. So that is the equations for the first flip-flop. See if I can get rid of these markings. Yeah, that's good. Let's move on to the next one. Okay, so we want, this is B next state right there, so we can say JB equal. So we're going to be looking at the case where B is equal to 0. So we're looking at this case here. And then we ignore the other one. So we make our circles now. So we see that we have x equals that, so we can say x, b can be, c can be either. B is no longer in this expression, but rather we use a naught. So the expression for this one is x times a naught. And then we move on to this other one right here. So when we add it, we see that x is 0 for both of these cases. So we say x naught. And we see that right here, a is equal to 1 for this. And again, we are ignoring these zeros right there. Just put it in red just to make sure we know what we're talking about. So we're ignoring those zeros, but we're only focusing on the a, and we see that a is, in that case, is 1. So we write down a right there. Okay, so now we move on to the KB. So here we're going to be looking at the values where b is equal to 1. So let's circle it again, just like that. And we are ignoring these here. So what do we got? Alright, we circled the empty spaces, as you know. So what do we have here? This empty space, that is going to be x naught, a, and then the second empty space right here, that's going to be x, because of this 1 and 1 right there, that one and that one, so that's just x, and a naught. So we actually see that these two are equal here. So to make our life easy, let's make them look similar. X not there, a naught rather. So they are the same. Okay, let's move on. We're now here. Let's just bring this up a little bit. So let's make our JK equations. So this is JA, and we're going to be looking at the case where A is equal to 0. So we're looking at this one, and we're looking at this one, and then the rest is cancelled out. So we see that every single cell here is 1. So what that means is we just call it 1. So let's move on to the KA now. We're looking at the case when A is equal to 1. That's this one here. We are ignoring the other ones. We see that we have all zeros in there, So we just circle the whole thing because we're circling empty space. Remember, when you're doing the k's, you're circling the empty space, not the ones. In fact, you're going to be circling the zeros. So once again, if you circle the zeros, it's all zeros, so we get 1. So let's rewrite our equations. Let's write them here on the right, starting with JC. So we have JC equal to KC x naught b times a plus x b naught a naught. And then we have JB equal to KB equal to x a naught plus x naught a. And then we have JA equal to KA equal to 1. So this is what we got. So now we have our equations, and we can simply move on to multisim now at this point. So it's important to interpret these equations when you're making your designs. So I'll show you how to do that in multisim now. Okay, so here we are in multisim now. I have the circuit here. You can see that logic gates are placed in specific areas, but I've disconnected them so that I can show you how to connect the logic involved in this circuit here. So let's just go over what I did here. I have the power, obviously, once again, coming in on the top and the bottom on all of the flip-flops here. I have my clock here on the bottom, 30 Hertz, and it's coming into the 1 pin, the 1 pin here, and pin 6 here. It's also labeled clock by the CLK numbers. So what else? This leftmost flip-flop is gonna be my A flip-flop, followed by B and followed by C. So that's how they're labeled. It's not labeled like that actually, but in your mind you can think of it like that. And once again, we are here. And these wires are hooked up to the decoder here. Looks like I'm missing a wire though, so I think it's this one right here. So let me hook that up right there. Okay, so now we want to hook up these logic gates, and we have to go back to our equations. I have them right here, the picture of it. So we have for JA, it says there it's 1 for both JA and JK. So all we do here is put that to the 1 and that to the 1. So, and obviously VCC is considered logical 1 because that is our source of power as well. So what else do we have? We have JB and JK equal to x times a naught plus x naught times a. So what does that mean? That means we have to grab x and a naught, place it into an AND gate. So that's what these AND gates are positioned here for. So I did this ahead of time, but now you can see how they work. So in this wire that I have here, I want x. So x is gonna be this one here. So since x, let's go back to this here. Since x is my input variable, I forgot to talk about this. This is my input variable, x. So then I have to make a switch here. So if x is if I want x to be 0, I leave it open. If I want x to be 1, I close it. So that's what this switch is. And the reason it's here is because I want it close to the display here. Okay, so now, so I have x coming into this logic gate here, and it also needs a not. So let's look at this flip-flop here. So on the top here we have the A coming out, and on the bottom we have the A not coming out. So rather than putting an inverter from this wire down to the bottom, we just grab it from here. And we take it there. So now here we have X times A naught, and that is also has to be hooked up to a OR gate because of this plus here. Doesn't look like a plus, but that's a plus. So what should be coming in the other end has to be X naught times A. So we want A into one of the inputs of the AND gate, and we want X naught. So remember, this is my X here, and I want the not version of it. So let's move all the way to the right, moving up here. So you can begin to see why I had these logic gates set up like this. And then we keep going. So we want, this is going to be JB and KB is equal to that. So, and they have to be added together. So let's do that. Let's add them together like that. And that is equal to JB and KB. So that's the input of the following flip-flop. So we hook it up like that. Okay, so let's keep going. So the last one, JC and KC. So we have, the first term is going to be X naught B times A. So it turns out that I can just grab the result of the previous logic gate and plug it into, not plug it in, but insert it into one of these legs of this AND gate. So which one do I have? I already have X naught and A. So X naught and A is this one. The result that comes out of this logic gate is X naught A. So I'm going to say, just going to wire that straight like that. And now I'm missing a B here. So the B comes out of this flip-flop. This flip-flop. This is the B flip-flop, right? So we have A, B, and C. So there we have it. The B and the X naught and A. So B, X naught, and A. Good. And obviously that has to go to this OR gate here. Okay. So what's next? The other one we want is we want X, B naught, and A naught. So we already have X, A naught. This one here is the A naught. This is the X naught. So why don't I just place a wire right here? Just like that, a straight wire. What else do we have? And we also need, which one am I doing again? I forget. We also need B naught. Okay, so I'm doing this one. I'm hooking up this last one up top. So I need B naught. So let's see if that's correct. So B naught, A naught, and X. Yeah, that's good. And so obviously that comes down, that this output is placed here. and they are the same output. JC and KC are the same, so this is going into the C flip-flop, both in the J and the K. And then there's nothing coming out of the C. We don't see the C variable here, so that's fine. The only variable, the only thing that we're concerned about is the output, which we do have to hook up to the counter, because this is what's counting. We have this output here. This is the most significant, and then this one here is the middle, and this one here is the least significant. Okay, so that should do it. So what I should expect to see here when I run it, I should expect to see the counter count up from 0 to 7, like we designed it. So let's see if that works. So it starts at 7, 1, 2, 4, 5, 6, 7. It restarts. Okay, that's good. And then if I hit the switch, let's see what happens. It's counting down. 2, 1, 0, 7, 6, 5, 4, 3, 2, 1, 0. And there it is. The up-down counter. If you guys have any questions, please leave a comment below. If you guys want to see me design one of these decoders, because like I mentioned last video, these components have, this component here in particular has a decoder that interprets the signals that are coming in here, and I can design one of those. So if you guys are interested in that, just let me know down below. But yeah, that sums it up, and thanks for watching.